Hi, welcome to you all for another presentation. Today, we will see the brief description or the brief information between the relation, the autocorrelation function, and then the power spectral density, right? The relation between the autocorrelation function. So the autocorrelation function is normally denoted by Rxx of tau, and the power spectral density is denoted by capital S x x of omega. Okay, so there is a important relation between these two, right? So Rxx of tau, this is called tau. This is nothing but autocorrelation function. This is called as autocorrelation. Okay, autocorrelation function. Whereas whereas this particular s x x of omega is called as, this is called as the power spectral density. What is that? Spectral power spectral density, PSD, also called as PSD, power spectral density of a signal or the input, right? There is very important relation between these two. Normally we can expect the problem in our competitive examinations like gate as well as engineering services examination, right? So see, for example, before going to give the relation between these two, a very fundamental, very important relation I would like to give you as that, let us say there is a system, there is a system, I am drawing like this. This is normally LTI system. What is this? It is an LTI system. What is LTI? LTI stands for linear time invariant. Linear, L stands for linear time invariant, right? Linear invariant system, right? It has different inputs, correspondingly it will produce the outputs, right? So it has different inputs. Okay, for each input it will provide the corresponding output. Sometimes your input can be a single variable, right? And correspondingly the system will produce the single output. Similarly, the inputs may be two or three or n number of inputs can be there, and the system will give you the n number of output, right? Say for example, let us say for example, so here my input is one particular. So here my inputs are the random variables. This is with respect to the probability theory and stochastic process subject what we are discussing now. Here, normally my inputs are the random variables, right? What is that? Random variables. Already, you already familiar with the random variables, right? So any random variable is denoted by either capital X or capital Y or capital Z. This we have already seen in our last presentations, right? So the random variable can be denoted by the capital letters X, Y, Z, and the possible values of random variable x are denoted by with a small x. Okay, the possible outcome values of the capital X are denoted by with the small x, maybe x1 comma x2 and x3 and so on and so forth up to xn you can write. Okay, and they must be denoted like this in these brackets. So x1, x2, x3 and so on and so forth xn are the possible outcome values of the random variable x. Similarly, if you consider y, the possible outcome values of random variable y are denoted by small y1, comma y2 and so on and so forth. You can write up to yn, small letters. Similarly, Z also. For this Z, only you have to write small z1, comma, small z2, comma, small z3, and so on and so forth, Zn. So this we have already seen, right? So here my inputs are the random variables. So for our simple example to understand this concept, I am considering the random variable x alone. Okay, I am considering the random variable x alone. So first, to understand the concept, then we will expand it to the multiple random variables, right? So I am considering the random variable x. Okay, random variable x. So for this random variable x, I am taking it as my input. Okay, for this random variable x, first of all, I should know about its autocorrelation. Let us focus on the topic which I am explaining now. Okay, so right, so I have to find out the autocorrelation. What is that? Autocorrelation. Autocorrelation function. Autocorrelation function of random variable x. So, what is the autocorrelation function first? Autocorrelation nothing but. So, the random variable x may have different possible outcome values, okay, at different instants of time. Therefore, therefore, the similarity between let us consider the random variable. Let us consider the random variable x at two instants of time. So at time t1 and at time t2, I am considering at two time intervals. What is the possible outcome value of my random variable x? Okay, so I am taking x as my random variable at time period t1. My possible outcome value of x is x1, and similarly at time 2 the possible outcome value of x is x2. Therefore, what is the similarity between these two? Is there any similarity? That similarity can be given as my autocorrelation function, and that is denoted by, there is a representation or xx of tau, or xx of tau. That is the representation. This is the identification for a autocorrelation function or xx of tau. What is tau? Time is the time difference. Tau is nothing but here. Tau is equal to, it is, you can write t2 minus t1, time difference. So where my tau is nothing but it gives the different time difference. It is the difference between t2 and to the t1, right? Therefore, R xx of tau, that is my autocorrelation function, right? So for the time being, just you focus on this alone, okay? In subsequent presentations, we will see little bit elaborate about these, parameters and the depth of, okay, these parameters. Therefore, the autocorrelation function of the random variable x can be defined as r xx of tau. So that is my autocorrelation function at my input side. And similarly, what is the power spectral density? Can the power spectral density is defined at the input? Absolutely. So the power spectral density, in short, I can write as PSD. Remember, it is the very important notation to be used for defining the power spectral density. P stands for power spectral density. So it is denoted by S, capital letter S, x x of omega. S xx of omega. Remember that the power spectral density depends on the frequency. Remember, very important point. The power spectral density is denoted by capital X suffix x x of omega. X is the random variable. X is the random variable. Again, X stands for the random variable, right? And it is depends on the frequency. Whereas the autocorrelation function is depends on the time difference tau. Remember that. So the autocorrelation function is denoted by Rxx of tau. Understood? The autocorrelation function depends on the variable tau, whereas the power spectral density of the random variable x depends on the frequency omega. Is there any relationship between these two? power spectral density and then autocorrelation function. Yes, there is very very important relationship between these two. Okay, before going to give you explain you the relation between these two, just I would like to uh, inform you that the power spectral density, which is nothing but sxx of omega, will be calculated both at the input side as well as the output side also, right? The power spectral density, what is this? It is the PSD at the input. Okay, the power spectral density can be determined, can be obtained at the input, as well as the power spectral density can also be determined at the output also, at the output also, right? Right. So therefore, let us say here the output, if my input is x, let us say, correspondingly I will take my output as y. Therefore, s x x of omega is the input power. Therefore it is, I can call it as input power spectral density. This Sx of omega nothing but input power spectral density with respect to the random variable x. Similarly, correspondingly, my random variable, my output random variable is capital Y. Therefore, with respect, this is my input. Correspondingly, the output random variable is Y. Understood? Correspondingly, the what is the output power spectral density with respect to the input? Obviously, S Y Y of omega. Any doubts? Okay, so I am taking as x as my input, input random variable, and for this input random variable x, correspondingly, I am defining the output random variable as y, because for the input x, what is my output? It is y. Just I am defining, right? This is my input, this is my output. With respect to x, the power spectral density is sxx of omega, xx of omega. Okay, correspondingly, the random variable y, the output power spectral density is syy of omega. Therefore remember that this is the output PSD. This is called as output PSD, power spectral density. I think one important point I have noted down here. What is that? So the power spectral density can be defined both at the input as well as the output. At the input, it is called as the input power spectral density. Similarly, at the output, it is called as the output power spectral density. Well, now I am going to give you the relation between the power spectral density to the autocorrelation function. Very, very important point here. Very, very important point. What is the relation between? Remember, the power spectral density PSD is equal to Fourier transform of your autocorrelation function. Okay, autocorrelation function. That's it. That's it. Remember this, very, very important. So this implies that with this I am going to stop this presentation. We'll see PST nothing but S xx of omega. At the input side I am considering Sx of omega is equal to Ft stands for Fourier transform of R xx of tau. Very, very important relationship. Therefore, my power spectral density is equal to Fourier transform of Fourier transform of autocorrelation function. So, if you know the Fourier transform, if you know the autocorrelation function, if you take the Fourier transform of that, you will get the power spectral density. And similarly, this is the direct form. Indirectly or inversely, the Rxx of tau is equal to, I can write like this also. Therefore, this is the direct equation, and similarly, my Rxx of tau is equal to, it is nothing but inverse Ft, inverse Fourier transform of S xx of omega. Therefore, if I know, if I know the power spectral density, if I apply the inverse Fourier transform to this, then I will get the autocorrelation function. So if you know the autocorrelation function, you apply the Fourier transform to that, you will get Sx of omega. Or otherwise, if you know the Sx of omega, if you apply the inverse Fourier transform to this, you will get your Rxx of tau. Right? So these two relations are called as Wiener-Khinchin relationship. Wiener Kinchin relationship, right? Now I am going to give you another very, very important relationship. That is nothing but what is the relation between input power spectral density and to the output power spectral density. Let us say, similarly, as I just explained to you, let us consider it as a system. It has certain input. Similarly, it has certain output, right? This is my input. This is the system actually. Normally, the system will have certain transfer function, Okay, the transfer function is nothing but h, also depends on the frequency. Let us call it as my random variable x here, and my output random variable is y here. And with respect to x, what is my input power spectral density? Sx of omega. Similarly, with respect to y, what is my output power? Power spectral density? S yy of omega. Therefore, the relation between the output power spectral density to the input power spectral density is gives rise. These are the three parameters you can observe. Input PSD, this is input PSD, this is the output PSD, this is the system function or the transfer function. Therefore, if you can define a relationship between these three, output power spectral density is equal to magnitude of h of omega square into input power spectral density. Very, very, very important formula. This is, remember, very important formula. Therefore, okay, this is what is this actually? This is my output PSD. This is what my output PSD, power spectral density. This is my input PSD, right? This is my input PSD. What is this? This is the magnitude of the transfer function or system function. This is called system function. Therefore, output PSD, this is the output PSD or system output. Okay, the output PSD is equal to input PSD multiplied by h of square, magnitude of h of square. This is the very important relationship between input PSD to the output PSD. I hope, okay, you understood this concept. What is the autocorrelation and the relation between input PSD and to the autocorrelation, as well as the relation between output PSD to the input PSD, right? So with this, we will finish off this presentation here, and we will continue the elaborate details in our subsequent presentations. Thank you. Thank you very much for watching.